And that's all we have presented on our poster over here. We have this 3D model exploded out. You can see each individual dead load, and then up here we start to get to the live loads for the rails, and we have the wind loads. He also did this for the longitudinal girder, which was kind of an extra for this, because all we really had to do was find the minimum height for the deck beam, which turned out to be 1.45 feet. So that qualified for this option, and got our bridge to statutory height. But the longitudinal limit, we have our dead load and live loads, with the Cooper load represented up here, and that was just kind of an extra that we threw in at the last moment because we kind of finished early. And the fatigue was not much of an issue. I'll let Zeb here explain a little bit more to you about that.
It turned out that well, fatigue can actually be a pretty important thing, especially when you're considering railroad bridges where you have a very high load, and then you have that very high load removed. So you have continuous loading and unloading, and that could cause failure in your connections. So what we did is we used the ARIMA code and analyzed the number of cycles for 100 years of service, which is our estimated lifespan of a new structure that we are designing. And we calculated that you would have to have 55 trains go over this bridge every day for 100 years to reach 2 million cycles. And today it's probably, we don't have the exact number, it's probably can't be more than 10. I'd probably say just a couple. Yeah, maybe 2. So we're way below that. And you can see here on the bottom left our allowable stresses. Because we're 2 million or less, we can have a much more allowable stress for our various members, our stiffeners, our joints, connections, our bolts, our welds can be lighter, and so this just gave us reassurance that we didn't have to go out of the way and design for fatigue considerations.
The final design that we came up with is represented over here in these elevation plan and section views. The bridge is 60 feet long to cross over Madison Road there, and our total width, which I believe is similar to what we started with, was 18 foot, and you can see that we've minimized our deck to 1.45 feet, allowing us the 13'6" clearance. Here's just an isometric view of the bridge. The colors aren't going to be what that's out of our heads. So now I think we're going to talk about some possible modes of construction.
Anytime there's a bridge construction, one of the big problems that cities and obviously the railroad would have a big issue with is lane closures and how long the track is going to be down, because they lose money by closing down the railroad. The city doesn't like closing lanes. There's a new technology that they've developed in the last 10 years or so, and actually started implementing it in the U.S. a lot. They're called self-propelled modular transporters, which are huge hydraulic jacks on wheels, basically. They've done interstate projects in Utah, and there was one case where they saved like $30 million, I think, because they only had lane closures for 3 days, replacing a bridge over for a huge interchange. And that's actually a picture of one of the pieces being moved. It's like massive pieces of bridges they can move in a matter of a couple days versus several months of closing down this lane and then reopening it, closing down this lane, and having the rails out for months at a time. You could replace feasibly this entire bridge in less than a week, probably, of downtime. And we actually have this, there's actually a simulation of what it would look like, kind of.
list over here.
You have it, just don't, you can't shit on it.
It was good. It was going.
You have to read.
Yeah, we're bulking up the. This is a two spans versus the single span. But so they just move in. They can take the old piece out. And just set in a new piece. Yeah. And actually, we looked into a possible laydown area because to use this technology, you have to have a laydown area that's near to the bridge. And this is Kenwood Road. There's like a bus turnaround area right there that would inconvenience the city buses, I'm sure, but in the long run, probably save a lot of headaches that they could use as a laydown area. And so they could just build the bridge there when they're ready, pick up the old bridge, lay it down next to it, and leave it there until it's ready to be demoed, and pick it up, put the new one in.
Okay, and lastly, we have what the finished product would look like. Before this bridge, I don't know if you can see here, but it's about 30 foot long, or 30 foot wide, and what we're considering is just a single lane, because it was a double lane. So this would actually push this bridge back, which you can't tell very much, but it is pushed back, and allow for a little bit more room up here. So this allows for a big ledge. So you would have to put a wall up here to keep people out and keep people from falling from up there. But this also creates a nice little place to do landscaping. And as we were told before, that this bridge could be a possible gateway to the city, or to Madisonville. So we put a kind of a landscape area here with welcome to Madisonville sign. The photoshopping skills aren't that great, but they can do. I mean, you can basically see where you could use improvements. There's actually a great big advertising sign right here, so all that could be cleared out relatively easily, and also on this side it could be done. And so that's basically what we came up with. Are there any questions?
Can you explain to me who was the structural designer? How are your cross paper, how are they connected to your, how is the transfer loads occurring?
I didn't design any connections.
Yeah.
I'm not even a structural major. I'm an environmental major.
Because that, particularly for railroad bridges,
Yeah.
that is the most